Okay, welcome everybody. This talk is about software testing, and the question is, can machine learning save us? It's a very bold question, but we'll see. We have been looking at this for a little while. Where we are, Carl Martin here. He's from Certus, which is the CMO Research Lab project that we're having. Certus is a center where different companies are partners, like ABB, Cisco, Kongsberg, Maritime, Kreftregisteret, and Cito. And Cisco is us. We have over 400 employees at Lysaker, engineers. So we're making video conferencing systems. That's where we come from, and we are doing a lot of projects together over many years. I think we have been working together with Simula for 10 years now. So, but me and Carl Martin have been working together for a couple of years. This talk, so we'll talk about a few things here. What are the main problems with testing today, and what extent will machine learning help us to address these problems? And also be looking at what kind of solutions exist, what people are actually doing, and what techniques they are using. And it's a huge area, so we have tried to cherry pick a little bit. So we'll look at the most apparent problems that people are addressing right now. So then also try to look into the future. What will it look like? So testing today. Well, just a little state of what software testing is. Of course you know, but just to make sure we are on the right page here. So it has to do with understanding the intent of the software and verify that it works. Create the test cases and report the bugs and fix them. So that's basically the operation we are talking about here. But the problems with testing today, they are huge, I think. The complexity is increasing all the time. We get more interwoven applications with cloud and everything, and the quality expectation is very high. If you deliver a bad quality application now, you're out of business. And it's a short time to market. People demand more features all the time. You have to come up with something new, or you're stuck behind. And of course, there's a high cost with testing. It's so high that people don't even dare to compute how much it is, I think, at least with Cisco. So this means trouble, really. But probably the biggest problem here is, I've taken this graph from a guy called Jason Arbon. This is the coverage gap. We know that when we add tests, we can do it one at a time. One guy is making one test and add it to the system. But we also add features to the system, and they tend to increase the complexity, because new features, they add more interactions with old features, so the complexity increases exponentially. And this is a problem we have to address somehow. And the question was that can software testing help us? Can machine learning help us try to cover this gap? So software testing has been standing still for many years. I've been working with testing for about 20 years, and it's basically the same we do today as we did 20 years ago. You know, it's you're creating test cases, you run them. We run them more often now, and they have more fancy execution systems and so on. But basically, it's the same. We add tests, we run them, and we fix the bugs. So it's a very expensive business, and all kinds of improvements that can make this more efficient is worthwhile doing. And that's what we see around now, that people are trying to use machine learning to improve the testing process. And also, the last years, machine learning has been creeping in all kinds of areas in software development, and also software testing. So why are we using machine learning at all?
Yeah. So to get a sense of why machine learning is becoming so popular, I wanted to give you a small little task. So here we have a bunch of faces from current and former US presidents. And if I ask you to group these so that photos of the same person are in the same column, you can immediately do it. And you immediately recognize who these people are, and it takes you less than a second to do it. You do it automatically, without thinking. But now I want to ask you, how would you teach a computer to solve this task?
First, you would add a microphone to yourself, and then you would start coding. If you do this with traditional imperative programming, right? Okay, if you only had to solve it for these 6 photos, then maybe you would get somewhere. But you would very quickly run into special cases, and the system would you'd have a very, very, very hard time scaling the system. But there are pictures of these guys, especially the guy furthest to the right, everywhere on the internet. So we can find a bajillion examples of pictures of these people. And this is where machine learning comes in. Because there is a lot of problems in our world today where we can collect a lot of examples of the type of behavior we want or the type of phenomenon we want to recognize. And that it's much, much easier to gather examples than to explicitly program. And that's where machine learning comes in. So machine learning is generally the field of creating systems that automatically improve the way they solve a task via experience. And experience can be either learning from data or receiving some type of reward in response to performing an action. So there really are 3 categories, or 3 main types of machine learning that you're likely to encounter. There's supervised learning, which is basically teaching a machine to solve a task by showing it a series of examples. There is unsupervised learning, where we ask the system to make an analysis solely by analyzing the data and finding internal correlations. And then there's reinforcement learning, which resembles more like how we train our pets. Every time they do what we like, we give them some reward, and every time they do something we don't like, we try to correct that behavior. And today we will show you examples of how these methods are used in testing. So as an example of supervised learning, we'll show you how certain companies are using that to improve the way GUI testing is done. And we will show you some of the work we've done ourselves using unsupervised learning for finding anomalies in test results and automatically sorting test results to make failure analysis faster. Then we'll talk about how certain companies are using reinforcement learning as an advanced form of monkey testing and to simulate user interactions. And I also want to mention that while I kind of cleanly delineated these techniques, in most systems you would want to combine them as well. Just so keep that in mind. It's rarely like a clean-cut black-white scenario. So yeah, can we drain the swamp of GUI testing?
Yeah, GUI testing, that's a mess. Everybody that's done that knows that this is a mess. Small product changes, which happens all the time, breaks the test. That gives you very high maintenance cost, a very little reuse of code. And also another problem with GUI testing is that you just check too little. You, for example, just check there's a box exists there and there's an icon there and so on. You don't check enough. It's never enough. But there are things going on here now. In one area is regression testing. Typically, when you develop a product, you add features to it, new features all along, but all the existing ones has to work. And when you add new features, they typically interact with old features, so they will affect everything. So you need a huge regression suite to make sure that everything is working well. So, and you cannot craft all these tests. And also, when we're talking about GUI testing here, exact pixel matching with comparing baselines isn't the way to do it, because there are always some small changes and you have to cope with them. And that's a lot of work as well. So, but there are people looking to fix this problem. So what they usually do is to detect the changes from a baseline, and you do that in smarter ways, not just pixel matching. You're just analyzing the pictures and figure out what are the major differences here, and they do this in a smart way. And that means that you can go beyond just pixel matching. And there are tools around already doing this. We have some called Apply tools and Chromatic and Retest they're called. So, but just to give an example, I've tested this Apply tools application on one of our screens. So this is a screenshot from our touch panel. We are making a system that makes calls usually. Most of the time. So this is a screenshot from one of our regression tests. And what we want to do is to compare this image with the next run of this test. So basically, so this is you see this run at 1916. So I run the test one more time. I want to do the compare of the images. So here's a lot of differences. This is pixel matching, very strict. All pixels are shown as difference, which is not very useful. You know, it's a lot of work to figure out this. But there is a second level, which is more not that strict. So you look away from a lot of changes, smaller changes. Still, it detects the time changes and the numbers are dialing here is also different. And also there's a way to match just the content of the text fields. So in this case, they detected that in fact dial different numbers, and also the time is different. But the last check is just to check the layout. That means just checking that there are no new icons there, or a lost icon, or some other problems. So in this case, the tool just accepts this as a correct image. And this happened without me doing any special configuration or anything. But with these tools, you can of course mark areas which you don't care about and so on. For example, if you have moving icons and things, there are troubles. For example, in this application, we have this. If you see this diffuse ball here behind, it's actually moving when you're doing the testing, which is of course troublesome to handle, but this tool actually handles it somehow. I'm not sure how they do it, but they claim to use a lot of image processing and machine learning stuff to do it. I'll try to figure out exactly what they do, but it's a bit secret sauce. But anyway, this is an example of a thing that will help. Another big issue with the GUI testing is test abstractions. You know, we told you that all the tests are breaking all the time because of small changes. They've been trying to address this problem for many years, but now there are more things happening. So the problem is the tight coupling between the application and the test. The tests become flaky. You know, GUI is always changing. We know that. Always some UX designers want to do some changes for good, bad reasons. But what is typically is that the scenarios that you're actually testing, they are long. They're living for a long time. So the problem is that GUI testing is painful, so you try to avoid it. So you try to test more and more just on the API, if you have an API, and that leaves that that you don't do as much GUI testing as you should. So that leaves that you have to do the manual verification of the GUIs, which is hard work. But the solution here is, you know, the idea is to create long-lived, high-level tests that you can use over a long periods of time through versions and different products as well. So the idea is to let the machine find the details by recognizing the screenshots and also look at the DOMs for the if you have access to the actually DOM for the web, for example. So just to give an example here, but the tools here are a lot of tools as well. Test AI is new players. Both of these first two here, they have recently raised a lot of money, so they're probably onto something. So just to give an example, in our case, we are making calls. That's a basic thing to do. So the test is like this: make a call, enter a number, and make the call, of course, and disconnect the call. If you want to do this in a regular GUI test, you have to find the call button, you have to find the field where you put in the numbers, and you have to press the call button, and you have to disconnect the call by finding the disconnect button. So, but what you can do is to train the system to recognize call buttons and the number fields and the disconnect buttons, and then you can run this test and let the machine find the right icons or the right places to click. So this is a trend that is really coming now, and a lot of players are doing this stuff. And in this way, you can keep your tests and just train your runner to recognize the elements. So.
Let's see. Okay. Thank you. So we want to abstract these tests, right? We want to make them agnostic to small, tiny changes in the GUI, and we want them to live long. So how could machine learning be used for such a task? Well, this will, at least an initial stab at the solution is to basically, first of all, gather a lot of screenshots of the type of UIs you're about to test, and some things that are relevantly similar but slightly different. The more the better. You would typically need 100 or thousands of images. The more the better. The more the better. And once you have those, there comes a big manual step of labeling that data, where what you basically need to do is you need to sit down and you need to select segments of the images and say this is a call button. And of course that's an extremely tedious and costly process, as I'll get into, but that's the next step. One way to achieve this is to employ something called AWS Mechanical Turk, which you might have heard of, which basically lets you hire people to fill in surveys as a service. It's very expensive, but it's probably more doable than doing it yourself. And once you have that labeled data, you can train a machine learning model to recognize these elements from screenshots. And then with that predicted model, you would basically, while running the test, feed running screenshots of the app as it is being tested to this machine learning model, which would then make predictions about the UI elements it sees. And if you then associate actions to those UI elements, i.e., if I see a login element, I'll try to register as John Doe, then you can use this prediction module to drive the behavior of the integration test. And that's the basic gist of how a player like Test AI at least claim that they do it. There's probably a lot more magic to it than this, but this is the general gist. If you can just collect enough data, you can do it. And so an important strategy here that we won't discuss in detail is what's called transfer learning, where instead of just having images from your own app, you gather data from tons of other apps to get a general idea as possible of what a login item is, for example. Right? And this is the technique that's used by Test AI, among others. So they've learned a neural net which is generic enough to recognize genuine UI components, and then you as a user can then train the network a little bit extra on the data that's exclusive to your domain, and then use that module to automatically drive your tests. That's the basic gist of how it works. So to succeed with supervised learning, the key is you need a very high quality data set. It has to have lots of entries, and it has to be correct, because if the data set is correct, is incorrect, your program will be incorrect. And you have to kind of find a way to construe the problem so that you can use these predictions to drive the testing mechanism. If you find that fit, then you basically have the things you need. And obtaining the data set is very, very costly. There's an interesting direction in machine learning now called active learning, which asks the question, if you have a limited data set, but you have a way of gradually acquiring more, what kind of observations should you search for? It's a bit beyond the scope of this paper, but I just want to let you know that it exists, and it's definitely worth checking out. So yeah.
Now we go over to the next topic here, which is
changing microphones live.
Yeah, analyzing test results in a smarter way. We have talked about this before. Also last year we had a wide talk about exactly this topic, so we just mention it here. But this is, when you do all this testing, you have to test all the time, a lot of test results. There you have got a huge bunch of test results, and of course a small portion of that will be failing. So, and also there's a fuzziness is increasing when you're doing system testing. There's so many things that might fail, and it also can be difficult to find a precise exact log failure message or failure cause that you want to look at. That means that you have to look in a lot of tests, a lot of the logs to find exact problems. So this is time consuming and boring. There's a lot of ways to do this, but in fact, just a side remark, at Cisco we also have a way of just grabbing true logs to find the patterns, to recognize failures. But this is a bit different way of looking at it, as using machine learning. Example here. Here we have a bunch of test results. Some are passing, the green ones, and some are failing. Well, we don't care about the green ones now. They are passing. They're also interesting, but not in this case. So we have a bunch of failing tests. And what you want to do is to identify the different ways these tests are failing. To my experience, there are usually many ways they are failing. So in this case, then we have different failures, different kind of failures. So they are collected together. These two are the same, and so on. So the idea then is to be able to automatically put this into buckets. Of course, you have to examine one of these instances of that failure. But then you will recognize the rest ones and put them in the same bucket, and you can avoid looking at all those other problems. So you can just check one, and you get the rest for free. Yeah. So just an example how this is working out in practice. Yeah. Sorry.
So how can you achieve such a thing, right? You know that there are some internal similarities in your test results,
that tests tend to fail for the same reasons, but how could you teach a machine to automatically recognize those things? Well, if you were to use supervised learning that we discussed earlier, you would have a problem with concept drift, in that your code is constantly changing, and the types of categories of failures will always be updated. And you play this cat and mouse game of always having specified the errors ahead of time before you can analyze your results. So how can we use something called unsupervised learning for this problem? Well, a kind of defining technique in unsupervised learning is what's called clustering, which is basically the task of taking data and grouping them automatically into groups by analyzing some internal attribute of the data. So in order to achieve that, you need a set of ingredients. First of all, you have to have a way of representing whatever you're trying to analyze in a way that you can actually cluster. And the key thing there is that you have to create a representation that you can impose a distance metric on, right? So, I mean, in a very, very simple scheme, you could just take the string edit distance of 2 logs and use that. But that's at least for logs that contain a lot of natural language, that can often be problematic. But another approach is what's called the bag of words approach. And when you combine these with the clustering algorithms, you have all the ingredients you need. Just to explain a bit how the bag of words works. Bag of words is basically that you try to create a vector representation of each log, and once each log is represented as a vector, as like a point in space, then you can easily reason about their distances. And then your clustering algorithm will say, oh, well, these points are close together in space. I'll assume that these are a group. And so it's kind of a contrived example. My French supervisor thinks this is a trivial example. I should not use it, but it's basically here there's 2 documents. One that just says, I want more chocolate, Mom. And the other one is, my mom and dad want more sleep. And we represent these. So each document gets its own vector. And basically, we've gone through all documents to find all unique words. And then we basically represent each log as, OK, out of all possible words that can occur, which ones are occurring and how often. And then you have a uniform representation where you can talk about distances. So for these 2 documents, you see that, well, they're similar in the sense that both mention the word mom, and they're similar in that they mention the word want, but they're different in that dad only occurs in the second document, and so on. We at Cisco, they use this to automatically group together similar test results. That was basically the idea behind what Marius showed you. It's a bit hard to see from this. It's more like here's a screenshot that proves we actually have a tool in production that solves this. It basically lets you, instead of having to process thousands of logs, you can process a cluster representative and then hope that, okay, by going through each cluster representative, you get an initially good view of what's out there, and then you can dig deeper if you need to.
I should mention that it doesn't work on all kinds of logs. We found out that after a while. Yeah. If the logs are too similar, and there are some issues with it. Yeah. But many logs with rich logs with lots of information in it, and then it works quite well.
Yeah. So I talked about the characteristics of supervised learning, and so the basic idea with unsupervised learning, there are other variants of unsupervised learning than just clustering, but it's a very, very common approach. And what we found at Cisco was that, okay, so we've clustered the logs and found these clusters, but when you do that, you've also found the anomalies, the points that don't neatly fit into groups. And you've made a system for analyzing those as well, right?
Yeah.
Yes. So you're basically solving 2 birds, you're killing 2 birds with 1 stone. You're grouping together similar things, and you're finding the logs that are particularly weird that you should have an extra look at. So how do you succeed with unsupervised learning? So the first thing to know is that we don't have a ground truth here, right, about how logs should be clustered. There's no fact of the matter of this is a more correct way of looking at it than the other. So you should only use these techniques when what you're looking for is not to make a prediction, but to simply have a different perspective on your data, where just having an additional perspective helps you, and that is enough. And you will have to decide on an evaluation strategy for unsupervised learning. And then there is a paradox, because if you had like a clear-cut evaluation strategy, then you would have the ground truth that you're kind of searching for, and then you would be advised to use supervised learning to get even better classifications. So there is an inherent paradox there with using unsupervised learning, and you have to find a solution that works for your organization. Yes.
Yeah. But there is more. So far, we're just talking about the low-hanging fruits, I think, making things simpler and faster and so on. The main problem here is still this graph. how do you cover this? This is just increasing. So the question is, you will never be able to handcraft your test cases, all the tests you need. So then the next question is, can the machine help us do some of the work? And that's what we've been looking at. This is probably the holy grail of testing. Is it possible to do this? And well, we're not there quite yet, but there are possibilities. And Martin will show you an example of that.
Yeah. So, I guess most of you have tried Candy Crush, the game, right? And the developers behind Candy Crush have done something pretty clever. They developed a bot that automatically plays Candy Crush. So why is this useful? Well, imagine that you have, it's like having a human tester on speed that can basically, first of all, just check that the level you created actually works, right? That it's possible for someone to beat the game. And also, when you run it, and so this is useful both for checking the productionized version of the app, but also during development, when you're trying to develop new levels and so on. And by comparing the performance of the bot to user level data, they managed to get some pretty good insights into the difficulty level of the levels. So they could make adjustments to the bot and make it behave like a really good Candy Crush player, a medium good Candy Crush player, or a bad Candy Crush player, and then see, okay, so how will people experience this level? Is it an easy level or a hard level, and so on. And when you have this tester on speed that's running Candy Crush again, you have a very, very efficient way of finding crashes. And it also, and when your program is stress tested in this manner, you also get to check performance. It looked like someone wanted to take a photo of the link. I really recommend checking out this YouTube talk. It's a great talk, and we will distribute our slides later as well. So yeah, don't worry. Yes, and so that's all well and good, but how did they do it? So the core technique for creating bots like that is what's called reinforcement learning. And to explain it, I want to go from the concrete to the abstract, so to speak. So imagine that we want to create a program that plays chess really well. So obviously then we have a chessboard and we have an agent, or rather our bot that we're trying to train. So to get started, we need to make some assumptions about our bot. First of all, that it wants to maximize some kind of reward, and that it remembers its history, it remembers the types of actions it has done in its environment earlier, and is able to optimize based on that history. And then furthermore, at least in the standard setup, we assume that there's some kind of control center or an observer that feeds the agent its view of the chessboard in this case, like it's saying, okay, well, okay, you performed E4, now the board is something. And when a given outcome is achieved, you can imagine it's doing a bunch of moves, and then perhaps he manages to do a checkmate. Then he will get a reward. And from that information, if you iterate this process thousands and thousands of times, since the agent has a way of remembering its history and optimizing for rewards, it will get better and better and better over time and make better and better and better moves. That's the basic idea. So the basic picture is we have an agent that is interacting with an environment and receives rewards based on the actions it does and optimizes those. That's the basic picture. So how do you succeed with reinforcement learning then? Well, clearly you need to have clear goals, right? So beating Candy Crush is a very, very clear goal. Ensuring that your app can't crash is a more hairy goal. So reinforcement learning in a testing context works perhaps best when you can use it as a kind of proxy for checking something else. So in King's example, they used a bot that just had as its only goal to be able to beat the game, as a driver for exploratory testing, for performance regression testing, and for analyzing level difficulty. Right? So they kind of solve the problem indirectly. And so if you can find a way to use reinforcement learning indirectly, you'll probably succeed. But in order to do this, your system really needs to be observable and fast. A problem that King ran into when they developed this was that Candy Crush didn't have an API that they could rapidly rerun against. They had to actually run the entire GUI and make the bot play the game. And this made retraining extremely tedious. So you have to construct your program in a way that a bot can rapidly interact with it in order to get this training speed. And obviously related technique is fuzzing, and there will be a talk on this fuzzer, American Fuzzy Lop, in this room in the next session. And it's a very related space, so definitely check it out. And then finally, there's kind of a thing we need to talk about, which is, so everyone's excited about machine learning, and machine learning becomes an integral part of our systems. It's not just something we use to test and to analyze user data, it's actually a part and parcel with the programs we're developing. What does that world look like? Well, so in the classic world, right, it was kind of like, okay, you have a program, and if you know its input and its state and the expected output, that's how you do testing, right? You check, okay, given that the program is in this state and it's receiving hello world, what do I expect to get out? And that's the basic testing image. But how does this image, what does this image look like when instead of humanly understandable source code, you have a neural net with carefully weighted, tuned weights? Well, the first observation is that the distinction between state and program, which can already be really murky in traditional software, gets extremely hard to make. That distinction becomes extremely hard to make. Because the program is essentially just a mathematical model that has been exposed to a very long history of inputs. And so instead of living in a world which is clear-cut, if you get a black input and you expect a white output, then that's what you got. You now need to reason about possibly millions of examples, and curating your data is just as important or even more important than curating your algorithm. And you reach a world where instead of looking at a single output, you need to think about ranges of outputs. And so it's definitely a very complex world where we're seeing the starting of now. There's a great paper that is freely available online, open sourced by Google developers, called Machine Learning, the High Interest Credit Card of Technical Debt. And they do a really good job of walking through different ways that you can create hidden feedback loops and how actually developing robust machine learning systems is extremely hard, where the types of problems we already have with our traditional systems, with creating good abstractions, separating concerns and so on, just get doubly hard in this machine learning driven world. So check that paper out. So the takeaways for testing machine learning systems, it is harder than ever to reason about the program and its state. And you need to have a shift away from validating code to validating data and to think in statistical models rather than algorithms. And then, so what about the future?
I don't know. Well, what's sure is that we get better tools, more abstractions. We see more of these GUI testing tools. Of course, certainly we see it's a coming of wave now of these tools. It will make your workday easier. But the bots, I think they were coming. They are all already coming, but there are no. You cannot buy any tools for that yet. So you have to make them yourself. But they will do the boring work, and the humans will do the guiding and the sanity checking of what these tools will output, I think. Yeah. And when it comes to testing the machine learning based systems, well, then it's more data driven.
Yes.
We have that problem ourselves now at Cisco. We have several sub applications in our systems that are using machine learning, like face recognition and voice recognition and things like that. Very hard to test. Very hard. It's the only way to testing is to test it, in fact, to use it. Put it into use and get feedback from the users. So it's a big challenge.
Yeah.
So yeah, I think that's. Otherwise, I don't know what's going to happen.
Okay.
So,
Well, thank you.
Yeah.
Yeah. I guess we are just about exactly on time, but we have time for some questions, I guess, if anyone has them. We're also going to stick around if people have. Yeah. Sure, yeah.
I have questions for Cisco.
Yeah.
Protocol testing using machine learning. Do you have tried this?
We don't do that. No.
You don't do that?
No.
No. That's not feasible at all? Or?
Probably feasible, but we haven't looked into it. I think it's probably hard work.
Machine learning in finding suspicious network activity?
Oh, that's a huge field. Yeah. Anomaly detection is what you want to look into. Yeah.
Well, there are so many fields. I think any field, so problems in validation and verification is a target for machine learning things.
Yeah.
Anything that can help you do this
Yeah.
hard work of doing it manually or making making your test by test doesn't scale. So you have to have it to do it.
Yeah. Any other questions? Yes?
We have this overhead of categorizing things you observe from the model. How complex does the software need to be before you have any benefit or?
Oh, you mean for using machine learning?
Yeah.
Well, I really think it boils down to what's most economical. Yeah. Is it gathering a lot of examples or thinking really hard about the algorithm, right? And if the answer is thinking really hard about the algorithm, then traditional software is best.
That was kind of the question. So have you had any experience?
I think, okay, this is just my personal opinion, but I think that in domains where you have to be exactly right? And where there are a lot of domain knowledge or developers with deep domain knowledge and know the business intelligence through and through, then I think traditional software development makes the most sense. But there are a lot of applications where you just have to be, right within a confidence interval, right? And that's where machine learning really shines. Yeah.
A couple of questions. You showed this GUI testing where you had where you sort of did abstraction and focused on scenarios. How well does this the current tools work when you have really long scenarios lasting for 10 minutes?
I don't know. But I think this test AI company, which is they are promising this now. So they are showing demos and things. I've seen videos of it.
Yeah.
And but your question was the same as I asked myself. This won't work in our application because it's so different. We don't make a shopping application or something like that. They have this demonstration on. But the idea of recognizing elements and abstract yourself from the exact GUI, that's going to come.
Yeah, but they have this kind of concept drift problem, right? In that they're trying to fit the world into, well, there are basically like all UIs exist of these 50 building blocks, right? But then you come, but we have a 51st building block, and they, well, we haven't trained our neural nets for that, right? You might end up in a situation like that, but I think also the insight, or an insight driving this company is that actually a lot of software UIs are basically the same, right? And they can exploit that to deliver their service. Yeah.
Another question, this log sort of clustering or also supervised training on logs is very interesting. But our logs tend to have quite a bit of false positives and false negatives. So they are sort of not of good quality. How does it deal with
well, we didn't say that, but we have to clean the logs before we do the clustering on them. We have to remove, for example, all the timestamps and all these words that are just making the word fuzzy. So a big part of the job we did with this was to clean the logs, to leave behind what's actually the difference, the words that are actually differing. And there was some cleaning process there that we had to do, which was in fact most part of the work.
Yes, but we also benefited from having, well, we have the raw logs, but we also have metadata that is separate from the logs, right? That is generated by the test runner that can say, well, we know that these and these assertions passed and failed and so on. So we have like side channel information that we can use as well.
On the unsupervised learning for the logs, do you use like a tool like you mentioned in the first case, or was it just machine learning libraries? Mostly kind of off-the-shelf open source scikit-learn. Yeah, Okay.
yeah,
It's
really.
quite, it's the code of running this clustering is.
Yeah.
No, it's 10 lines.
Yeah, last year we fit the entire code on one slide, so it's quite easy.
So it's more about understanding your data and tuning your data.
Yeah, it's like pushing the magic button and something comes out, and it's all in your data, right? So, yeah. Any more questions?
Okay, thank you.
Thank you.